Okay folks, so welcome to the first lesson in our new topic, and in it we're going to be looking at trends in the periodic table for a variety of things, and we have to be able to state what the trend is and explain the reasons for that trend. So for each of these trends we have to know what happens as we go across a period and down a group, and the ones that we're going to look at in this topic, in this section at least, are atomic radius, a thing called ionization energy, Group 1 reactivity, which we did ways back, and Group 7 reactivity. So we have to know what happens as you go down a group and the reasons for it, as well as what happens as we go across a period and the reasons for it. And when we go to bonding topic, we will look at the trends in electronegativity. So the thing that we're really going to focus on today is what happens to atomic radius down a group and across a period. So atomic radius, in normal person speak, it would mean the radius of an atom. So if this is a circle, this is the radius. Unfortunately, in atoms, we can't tell the atomic radius as simply as doing a piece of maths using an electron microscope. And we'll refer you back to when we did the Bohr, the limitations on Bohr. We had things about knowing the position and velocity of an electron, and we had issues with the fact that electrons behave as both waves and particles, and they interfere how you calculate atomic radius. So for that reason, what chemists do is they take half the distance between the nuclei of two atoms of the same element, joined by a single covalent bond. And this is going into your yellow book. It's page 123 on mine. So I always write it as 3 lines because sometimes it can be 3 marking points, and the things that people omit would be of the same element, and they always forget this line, joined by a single covalent bond. So if I can't measure the position and velocity at the same time, then this boundary here is very diffuse. Similarly, if electrons behave as both waves and particles, then when it's in a wave form, how can I figure out where the boundary is? So we take 2 atoms of the same element, and it's half the distance between their nuclei. So you pause as you need to. I'm going to move on. So the reason why it's hard to measure the radius are for the reasons that we've said. It's impossible to measure the position and velocity of an electron at the same time. So to remind you, this is Heisenberg, his uncertainty principle. And the second reason is electrons behave as both waves and particles. So for that reason, you can't figure out where the boundary is. And this was de Broglie came up with this. So these were our limitations for Bohr, and now we see that they have another application. So you have to be able to explain now what happens to atomic radius as you go across a period and down a group. And you have a table that looks like this on your page 123. So if we start here and we look across, what can you see is happening to the number? So as we go across a period, your atomic radius appears to be decreasing. So it's decreasing as we go across, and what's happening to it as it goes down? And if you look here at group 1, you can see that your atomic radius increases as you go down a group. So I have flipped over the page to 124, and this is just another visualization of it, showing you the size of the atomic radius, and you're interested for you. So atomic radius decreases across a period, and it increases down a group. So please get that into your head sooner rather than later. Now, this is telling us the same thing, it's just telling it in a slightly weird way. So if we have a look at these elements, that are up here. So this is element 3, this is 11, this is 19. So here, these peaks, 3, 11, 19. If you have a look at your periodic table, you've got one in the front of your yellow book and one in the back. So what is it that these things are telling you? So for starters, what's happening to the atomic radius for these three, it is increasing. So your atomic radius is increasing here. And if you look at what these elements are, this is the elements that are in group 1. Now remember, hydrogen is weird. So these are your group 1 elements, which means these guys here must be the period n is equal to 2. So this is your period is n equal to 2, this is your period n is equal to 3, and this is your period n is equal to 4. So atomic radius increases down your group, and your atomic radius here is showing you that it is decreasing as you go across a period. So it can be helpful sometimes to get familiar with these kind of funky graphs, because the SEC may use them and they'll ask you to interpret it. So work out what you think you can. So always look for where is group 1 in a graph, and then where is period n is equal to 2, and that can sometimes help you. So if you might like to annotate your equivalent graph, and the blurb we want is that it's showing that atomic radius decreases across a period, which is your peak to trough. And it's increasing down the group. Which is the peaks. So that's going to go in the space underneath the graph. So again, this is just another visualization showing you the numbers. It doesn't have the transition metals in here, but you can see it is increasing down your group and it is decreasing across your period. Now the SEC are going to ask these questions as state and explain. So it's going to ask you to state what happens to your atomic radius as you go across a period and explain that. So the state part is easy. This is the state. Atomic radius decreases across your period, and it's now we have to do the explain. So this is the new learning. So the reason why is that as you go across a group, you're getting an increase in nuclear charge, and this is how I would like for you to put in your answer to that question. What does that mean? Well, if we take lithium here has 3 protons. This has 4 protons, 5 protons, 6 protons, 7 protons, 8 protons, 9 protons, 10 protons. So as you're going across the group, you have this extra positive charge, and the more positive charge you have, the better that is at drawing the negative electron shells to it. So chemists describe that as an increase in nuclear charge. And the other thing that we're going to put in here, and I'll explain it in a while, is that the screening effect stays constant. And what that means is there are no extra energy levels. So I'm just going to draw my positively charged nucleus here for you, and we have your first electron shell when we draw our old school Bohr diagrams, and this, so the first one is this one here is n is equal to 1, and the one we've just drawn is n is equal to 2. And what we have is the fact that every element or every electron that's going to be added across period 2 is going to be added to this particular shell or particular energy level. So at the moment, if this is my nucleus, then the n is equal to 1 is screening n is equal to 2. But every electron I'm adding here is going into the same energy level, so it's the same screening effect. So you got to bear in mind, bear with me now on that, and I will explain it, I'll try again in a little while. But the things that that's your state, these are your explain. So an increase in nuclear charge and your screening effect is constant. and I will come back and explain this a little bit more. So equivalent for what happens down a group. So our atomic radius increases down the group, and that's your state. And what is your explanation? So as you go down through each group, we are adding extra energy levels. So there's an increase in the number of filled energy levels. So if we look at potassium through old school Bohr diagram, positively charged nucleus, we have 1 electron shell, 2 electron shells, 3 electron shells, and finally the 4th. So now I have an increase in the number of energy levels, which explains why my atom is getting bigger. And what we also have is there's an increased screening effect. So what does that mean? This is my positively charged nucleus. For the nucleus to affect this electron out here, there's 1, 2, 3 barriers between it, and that's called your screening effect. So we saw here, if you just go backwards, we saw here that the screening effect remained constant because every electron was added into the same energy level, whereas here now, as we go down the group, we are adding in extra energy levels. So the atomic radius increases going down a group because there's an increase in the number of energy levels and there is an increased screening effect. Now in reality, some of you may also say, but miss, your nuclear charge is also increasing. So which is true, because here I have 1, 2, 3 protons, sodium has 11, this has 19. There is an increase in your nuclear charge, but we don't use that in terms of our explanation. The fact that you get more energy levels kind of offsets the increase in nuclear charge. But we'll just put it in, but this is not a marking point. Okay, so it's only these two guys are your marking point. So at this point, I'm just going to have a little look at your screening effect and see can we explain it better. So as you go down, these are group 1, and as you go down a group, you get an increase in your atomic radius. Now you have this better in your book than it is drawn here. So what is this showing? So lithium, its outside electron has 1 barrier, has 1 shell between it and the nucleus. So 1 shell between outer shell and nucleus. If we look at sodium now, so this is my positively charged nucleus. I now have 1 energy level, 2 energy levels, and finally the last electron is in the 3rd energy level. So there are now here 2 shells between the outer and your nucleus. So that is your screening effect, the fact that you're getting these extra layers between your nucleus and your outer shell. So as in earlier with potassium, we're now getting 4 energy levels between, 3 energy levels between, 3 shells or 3 energy levels between the outer and the nucleus. So there's way more screening. So screening is increasing as you go down the group. So your atomic radius is increasing as you go down the group, and the screening effect is increasing as you go down the group, and that's because you're getting more energy levels between your outer electron and your positively charged nucleus. Now, can also put this in. The extra energy levels of the electrons blocks attraction of the positive nucleus to the outer energy level electrons. So I've just put that in context of one shell between your outer electron and nucleus, or 2 shells or 3 shells. Now if we were in school, let's get to the floor diagram. So if we had been in school, even though the way the desks are arranged we can't see it now, but in school the way I have drawn it, and I'll draw it from, if this is my teacher desk is the positively charged nucleus, and what I have done was I have put, if memory serves, lines of tape, getting closer together, trying to do it as well as we can. 1, 2, 3, 4, 5, 6 and 7 on my floor. So this is the door into my room. So this is the first energy level, second energy level. So this is like the Bohr, explaining the Bohr blurb. N is equal to 6, N is equal to 7. And as we go back, so if we take the example of, this might be lithium, sodium, potassium, rubidium, and right, no, I've done that wrong, so apologies. So we go lithium, sodium, potassium, rubidium, scandium. So as we're going down, this is going across, this is our group 1. And as we go down the group, the atomic radius so my atomic radius is increasing and my screening is increasing. And my number of energy levels is increasing. Okay, so each of these, so if I'm interested in lithium, this line, the N is equal to 1 is its screen. If I'm looking at sodium, the N is equal to 1 and the N is equal to 2 is that screen for its outer electron, and so on as you move backwards. So atomic radius increases, and this is showing you your screening effect. If we then were to take our lithium and we were to go now across group 2 and we were to put, so lithium is 3 positives, nitrogen is 7 positives, all the way to neon, which is 10 positives. So this now is going across a period. And what we find, so the rule is for across a period, your atomic radius decreases. And the reason for that is because you get your increase in nuclear charge. So you're adding a proton as you move across. But the screening effect is the same because there's only this N is equal to 1 between everything, every element from lithium to neon. So that's why we say the screening is constant. Okay, so that's where we're going to leave today. If you have any questions, obviously you need to get in touch. So I will be on the Zoom call, so you can get in touch that way. And homework will be as an assignment with the class notebook link. Thank you.